Hey, Dr. Dean. Miss
Uh-huh.
Dean.
What's up?
Are you still like paying the videos of the classes too?
Yep.
All right. When is our test?
Next test is going to be next week.
This week. All right. And then our final exam is on.
Final exam week is May. For non-seniors, it'll be May 4th through 6th. For seniors, it will be not next week, but the following week. So I was going to explain how all the test stuff is going to work on Monday. So, because we have to have senior stuff in a little bit earlier, so they have slightly different things. I don't know if we have any seniors in here, but I'm just doing it streamlined across my classes so that everything fits together. But good questions. Give everybody a minute or two to get in. So go ahead and all right. So today we're going over 12.1. No, this is not learning how to count. This is not that kind of counting. But yeah, topic of today is going to be basic counting principles. And believe it or not, it is actually kind of a big deal, especially in the cybersecurity world of today. Well, let's start off with an example. Suppose a person is forced to make a password that must include at least one capital letter, one lowercase letter, one number. For simplicity, we will assume special symbols cannot be used. How easy is it to guess an 8-digit password? Assumptions that are more true than you may think. The capital letter is the first character, and the number is the last character. So this is pretty much true across the board. People are very used to having capital letters at the beginning, and then they usually put their name or something, and then I don't know, their birthday, or 1, 2, 3 at the end, something like that. So this is something that is pretty common, and with computing getting to the point where it is, suppose you can check 1 billion passwords per second. Okay. So how many different passwords can we have? And this is what we mean by counting. All right. So any idea how we might even try to start answering this? So let's take it back and simplify things a little bit. We'll use our basic problem-solving concepts we talked about at the beginning of the semester. Suppose your password was a single letter. How many passwords could you have if you had a single letter for a password?
A lot.
A lot?
26.
What was that?
26.
26. Why 26?
26 letters in the alphabet.
Because there's only 26 letters. Exactly. Very good. So if there's one letter, you have 26 possibilities. Well, what if the password was one letter and one letter, or 2 letters? How many passwords could you have then?
Would it be 13? You
No.
said 2 letters?
Yeah, there's 2 letters. So how many passwords could you have?
24.
Hold on.
So how about we say, if your password is one number, how many total passwords could you have if your password is just a single digit number? It's not,
Nine.
it's not a trick question. What'd you say?
9.
Close.
10.
10.
0. Okay.
0. Perfect. Yeah. Yeah. It's one that people forget. Poor little guy. But yeah, so you could have 10 total passwords for that thing. So you can have 0 through 9. But maybe I should say not one number, but one digit. What about 2 digits? So to phrase the question a little bit differently, how many different numbers can you make with 2 digits?
Is 89?
Almost.
90.
What did we forget the first time?
It would be 100, right?
100. Yeah. 0 through 99. I guess if you want to keep all the digits there, it'd be 0 through 99. So what about so 10? What about with 3 digits?
Zero 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 2 999. So basically 1,000, right?
Exactly 1,000. So the idea is for each location, you have a certain number of possibilities for that space. So for each one, if we're just doing numbers, there's only 10 possibilities. But when you combine them, you increase the number of possibilities. So how did they increase? Is there a way we could take this and get, sorry, forgot a 0, and get this? What is 10 equal to? It's kind of a stupid question. It's equal to 10.
Yeah.
What is 10 times 10 equal to?
100.
What is 10 times 10 times 10 equal to?
1,000.
1,000. So when counting, the number of possibilities you get that you could put there is the number in each case multiplied through. Okay, so let's take this idea and apply it here. We said that the capital letter was first and the number was last. So how many capital letters are there?
It can be,
It'll be 26, right?
26, yeah. Very good. Okay. How many lowercase letters are there?
26.
So 26, 26, 26, 26. How many digits are there?
Would it be 10?
Yeah. There's only 10 possibilities for a single digit number right there. So the total number of possible passwords that you can make times. And this seems like a huge number. So there are 318. So there are 80 billion 318,101,760 different password combinations that you could make from this 8-digit thing. So how long would it take our little computer to check, to plug each one in, check to see if it was right, and then move on? Assuming it was the last one that it checked, how long would it take? So how fast did we say our computer can check?
Billion per second.
1 billion per second. So what is 80 billion over 1 billion?
$80 billion, right?
What's 80 billion divided by 1 billion? So this is one that maybe is
80.
what?
80.
80. Yeah. So it'll take about 80 seconds to break your password. Not real secure, is it? And 1 billion passwords a second is not that fast. I mean, it's a big number, so it seems pretty fast. Let's see. Wanted to check something, but didn't have enough time before class. So the new Ryzen chip, which is a home computer, can put out about 14 teraflops, which means 14 trillion operations per cycle, which is, it could break this down in a matter of, I mean, it would take you longer to initialize the program than it would for the program to actually break it, is what I'm saying. So this is not a very secure password, but this is kind of an introduction into how counting things works. I've got a fun little comic. So in this comment, they break down how secure a password is. So this is an older comment, but if you just have some random assortment of numbers and letters, not even the simple ones like we had a second ago, but very randomized, you have, there's some higher level sciencey talking about bits of entropy of information and stuff. But the thing to take away is at 1,000 guesses per second, it would take about 3 days to guess this ridiculous password. However, it's easy to guess, but it's hard to remember. Troubadour, okay, where's the 0? Where's the 4? The ampersand, the 3? What, like, where does all this junk go? But for random words, because of the sheer size of it, and it's a long password, it would take, again, at the same rate, 1,000 guesses per second, it would take 550 years for a computer to guess that, which is very hard. But for you to remember just some silly words, not that hard at all. And it's funny that through 20 years of effort, we've successfully trained people to use passwords that are hard for humans to remember, but easy for computers to guess. And that, this is, any of you guys who enjoy nerdier comics, this is XKCD, and it's fabulous at these random thoughts that just pop into his head, and he just goes after it with a nerd that pretty hard. So back to our situation here. The primary means of counting problems is to break down into simpler problems. This is kind of reminiscent of where we started at the beginning of the semester, is taking a difficult problem, turning it into an easy one, and then slowly piecing it back together. So example, a guest at a catered meal has a choice between 5 entrees and 3 desserts. If a guest's dinner is entirely determined by these choices, how many different dinner choices are there? So, you're at a wedding or something, and you have 5 entrees and 3 desserts to choose from. How many different possibilities can you have from those options? Well, we can do it the old-fashioned way, which is add them all up. So, it's about dead. Chicken, fish, beef, vegetarian, and let's say pasta. Cake, ice cream, and I don't know. So, how many different choices are there? So in this visual way, we're getting into graph theory, but you could choose the chicken, and with the chicken, you can get the cake, the ice cream, sherbet. You choose the fish with the cake, ice cream, sherbet. Beef, cake, ice cream, sherbet. Vegetarian with cake, ice cream, sherbet, and pasta, the cake, ice cream, sherbet. So, how many combinations are there?
Is it 15?
15. Yeah. So we have 15 total combinations. So you may be tempted to just do it like this every time, or something like this, write out all the different combinations. But you quickly find that that's a rough time. We should just continue to do it like we did our previous problem. So how many possibilities are there to go in this entree space?
5.
How many possibilities are there in the dessert space?
3.
Very good. So the total number of different possibilities we can make from 5 things in this space and 3 in this space is 15. And this brings us to our fundamental counting principle. Suppose we can break a counting problem into 2 or more tasks. If the first task can be performed in m ways, and if after the first task, the second can be performed in n ways, then the first task followed by the second task can be performed in m times n ways. This method is often, though, thought of as multiplying when you're performing steps. Okay. Important to note in these problems, the order does matter. We'll not discuss how to solve problems when the order does not matter. I'm not sure about extra credit assignment. You'll got a lot going on. So, for example, if a home security code consists of a sequence of 2 distinct letters, A to Z, then how many different codes are possible? And if a thief could try only 5 possible codes every 30 minutes, how long would it take the thief to try all possible codes? Okay. So, how many operations or events do we have in this problem? Did I not share that? That's silly. Okay. So look at it again for a second. Suppose we can break counting problem into 2 or more tasks. So we're doing 2 things in a row, 2 different things. We can do, in the first thing, there are M possibilities. And in the second thing, there are N possibilities. So kind of like what we just did with the number of desserts, or the number of entrees, and the number of dinners. So the home security question is a code consisting of 2 distinct letters, A to Z. How many different codes are possible? And then if a thief could try only 5 codes every 30 minutes, how long would it take the thief to try all possible codes? Well, let's answer the first one. How many different codes are possible?
Would it be 26?
So if we have a single letter code, then it's 26. But it's a 2-letter code. So what do we do? How many slots are there? It's not just 1, there's 2. You have to put in 1 letter and then another letter. So how many possibilities are there?
Would it be 52?
No.
I don't know.
So there's 26 possibilities for the first letter. You can pick any letter, A to Z. But then they have to put in a second letter. So how many possibilities are there for that one? So this is just like all the stuff that we've done so far. "26 letters for the first one that you enter. If it was just a 2-letter code, then there would also be 26 possibilities for the second thing. But in this case, there's a little extra piece. In this case, we're talking about a sequence of 2 distinct letters, meaning you can't have any repeats. So if that's the case, then how many possibilities are there for this one?
I don't know. I think would it be 25?
It is 25. Yeah. It's all of the letters except the one that you already used. So times 25. So when you multiply that out, you get 650 different combinations. Okay? So what about if the person can try 5 codes every 30 minutes? How long does it take? Well, if they can try 5 codes every 30 minutes, how many codes can they try in an hour?
Ten.
Yeah. So 5 codes per 30 minutes. We're going to convert this to 10 codes per hour. So 650 is like 2.5 days. Maybe a little bit more. Point being, it would take them a long, long time to try all of these possible values. All right, let's try another one quick before we head out. A 2-digit code is constructed using the digits 1 through 4. If the second digit is required to be at least as big as the first one, how many codes are possible? Actually, we're going to keep that one for next time because we're going to be running a little bit short, and it's actually a very interesting question. So how about this one? If we roll 2 distinguishable dice, how many outcomes are possible? So we've got 2 dice. How many outcomes can you have?
Would it be 36?
Yeah. So we're talking about 2 distinct events. How many possibilities are there for the first dice roll?
6, right?
6, yeah. And they are 2 distinguishable dice, just means that you can tell, like, one's a red die and one's a blue die or something like that. So otherwise, you wouldn't be able to tell the difference. And so like a 6 and a 1 is the same as a 1 and a 6, but we can tell the difference. So how many possibilities do you have for the second dice?
6.
Yeah. All right. So, yeah, that's good for right now. We will continue on with the rest on Monday. Yeah, so everything is still getting uploaded to YouTube. So if you need to go back and review anything, go there. But also these notes are posted on your Ginzabar, so you can look at them, follow along, that kind of thing. Highly suggest you do that. Don't even have to print them out or anything. But if you have any questions, I will be at office hours 12 to 1 and 2 to 3 today. So, all right. Well, you guys have a fabulous weekend. We'll see you all on Monday.